lithium, sodium, potassium, cesium. These are all examples of the alkali metals. The alkali metals lie on the left-hand side of the periodic table, with the exception they do not include hydrogen, which is a gas. They're being a part of the metal family, they all exhibit characteristics of good conductors of both heat and electricity. But these metals in particular are particularly soft, with very low melting points. In fact, as you move down the periodic table, they become easier and easier to melt at lower and lower temperatures. Chemically, they're the most reactive of the metals. We'll take a look at their particular reactions a bit later on. But what is interesting to note is as you move down the table, the reactivity increases. We can explain this by taking a look at their electron configurations. First of all of these species have an effective nuclear charge of +1. However, as you move down the family, they have increasing numbers of energy levels. That places that valence electron at a more distant orbit, making it easier to lose, hence lower ionization energy and greater reactivity. They tend to form ionic compounds when they react with nonmetals. For instance, table salt is shown here. All of these species tend to lose that S1 electron and develop a +1 charge when they form an ion. Let's look particularly at the reaction with water. Here's a picture of potassium reacting with water. Now the pink color that you notice there, that doesn't become evident unless you add a chemical indicator to the water. That chemical indicator is showing the presence of what we call a metal hydroxide. That metal hydroxide changes the indicator from a colorless to a pink color. In this case, phenolphthalein is the indicator. So a metal and water will produce a metal hydroxide. They'll produce hydrogen gas as well as heat. Here we have the unbalanced chemical equation. To balance it, we'll need a few coefficients of 2 to balance out the number of atoms. And I want to introduce at this point something called a net ionic equation. Species that are aqueous, in particular ionic materials that are aqueous, will tend to break apart into ions when placed in the water. So here, my metal hydroxide, when placed in the water, will break into the M+ ion and OH- ion. I now have what's called a net ionic equation for this reaction. I can then replace the metal ion with any of the alkali metals. Alkali metals also will tend to react with nonmetals, and they will tend to form a group of compounds that are called salts, and this again is a picture of common table salt. So let's take a look from the metal side. We'll use sodium as our example of the alkali metal with a 3s1 valence electron configuration, and chlorine from our nonmetals, which has a 3s2 3p5 configuration in its valence shell. Sodium will lose that 3s1 electron, donating it to the chlorine, and thereby the species will then have a complete and stable outer electron configuration similar to that of argon. And that then develops the charges on our two species. These have opposite charges and will tend to attract each other. This is the nature of an ionic compound. Here is the chemical equation for what went on, and here's the balanced chemical equation for what went on. It's important that you be able to write some of these chemical equations, in particular the reactions of the alkali metals with water and the alkali metals with our halogens. I hope that helps, and comments are always welcome.